Hello everyone, welcome to Theory of Computation GTQ 2022. So this is GATE through questions, important questions that will appear in GATE. So what we are going to do today? We are going to have a session of about 1.5 to 2 hours in which we will be doing problems of the type that will come in GATE. So it will provide for a last minute revision of concepts. So I have carefully chosen the questions so that it falls exactly in those areas which are very important for the subject TOC. Now the major areas, first of all TOC, half the questions come from chapter 1, that is finite automata, regular languages, regular grammar and regular expression. So the most important of all is regular expression. And the next thing is the FA design, and also we will have a sprinkling of some question of FA to language or language to FA, I have chosen. And then what are the other areas of importance? This is what is very important in the chapter 1. Then so I have taken some questions from that. The next is closure. Year after year, particularly in recent years, questions in closure are repeatedly appearing. Then we also have given a PDA, finding the language. Recent years these questions are coming from this area also, PDA to language. So we will do a question in that. Then PDA theory. By PDA theory I mean questions, true or false questions related to ambiguity of grammar, ambiguity of languages, derivation tree, this type of things. So we will do some questions in that. And when we come to last chapter, Turing machines, here we will do Rice's theorem, advanced Rice's theorem question. That is basically identification of language. Which of the following is decidable, or which of the following is RE but not REC, that type of questions. Lastly, reductions. Reductions is very important. So the questions we are going to do today will be nicely spread out in this, at least 2 questions in each. Roughly we will do 15 questions at least. And so that's what we will be discussing today. Okay. As I am writing the questions, please try to solve it and then I will write the choices. Okay. Wherever it's MSQ I will tell, otherwise it's MCQ. Most of them are MCQ. Wherever if it is multi-select question I will tell you. Okay. Let's move forward now. Let's start with question number 1. Question number 1. We are starting with a question of FA, that is chapter 1. First we will do some questions from chapter 1, then chapter 2, then chapter 3 in that order. We will do FA to language this time. The following DFA, I will write only the essential part of the question. Okay. When you read in the exam also, read the essential part. The following DFA accepts which language on the alphabet sigma equal to 0, 1. Sometimes they will say on 0, 1 whole star. That means the alphabet is 0, 1. Or they will directly say on sigma is equal to 0, 1. Same thing. So this is a question of given a DFA, finding the language. FA, that is M to L question. Now let's see what the DFA given is. The first state itself is final state. Every state, DFA means every state will have 0 and 1. 0, 1. This state 0 is going here, 1 is going here to a trap state here. Notice where is the trap state always when you see the machine. Sometimes they will say DFA, sometimes they will just say FA. In that case you check it, maybe that FA is a DFA. How do you check it? Make sure every state has got 0 and 1. And make sure there is no null move. Here 0 is going here, 1 is going here, 0 is like this and 0 is going here and here 1 is going here. This is the machine. This is clearly not a standard machine, but it's a variation of the, usually they give variations. You have to adjust to variations. In chapter 1 you have to adjust to variations of the things we have done in class. But how do you do it? You can do it through counterexamples. When you see variations, you can do it through counterexamples. First try to directly figure it out, otherwise you can use counterexamples. The counterexample method is very powerful. It can be used in regular expressions as well as in machine. Okay. Everywhere it's useful. Okay. What are the choices given? A, B, C, D. 4 choices. Multiple choice question. We have to find the language of this DFA. So try to find it before I write it. First, even number of ones. Second, even number of ones with extra conditions, variation, and every one is followed by exactly 1 0. Exactly 1 0. That is choice B. Choice C is even number of zeros and every one is followed by at least 1 0. This is exactly 1 0, this is at least 1 0. This is even number of ones, this is even number of zeros. The last is even number of ones and every one is followed by at least 1 0. So this part is same in this and this. Same, at least 1 0. Every one is followed by at least 1 0. But the difference here is this even 0, this even ones. Between these two, you have to see the difference between the answers. This even ones, this even zeros. Here it's exactly 1 0, this is at least 1 0. This is just even ones. So what is the answer here? How to do it? Scan through it one by one. If you want to throw out the choice, if you directly know the answer well and good, but otherwise you can, I'll show you systematically in the exam. Of course, you will not do each of the steps. But right now we have time, I'll show you how to think about it. How to throw out the answers. You can throw it out by counterexample. What is a counterexample? There are 2 types of counterexamples. To throw a language out, one counterexample is make it reject a member. Finished, that language is then wrong because it has to accept every member. Or make it accept a non-member. These are the 2 types of counterexample. Here what we can do, even ones. Even ones, actually what is going here is even 1. So try to make it, see the smallest example of even 1 is 1 1. Null string of course is even more smaller, but null string is accepted, so it's not a good example, good counterexample. But 1 1 is getting rejected. That is the smallest even 1. Always choose counterexamples in a very simple way. Okay, don't take lengthy counterexamples, small counterexamples, simple things, simple members. Simple member is epsilon, but that's accepted, so it's not a good one. Let's take the next simple member is 1 1, rejected, so finished. Even if 1 member is rejected, you can throw it out. Then even ones and every one is followed by exactly 1 0. Even ones it's difficult to find counterexample because whatever is going through, see here, it has all even number of ones, see 1, 2, 1, 4 ones. So try to attack the other part. Every one is followed by at least. This is actually what it said. This is even zeros, not even ones, even zeros. Even zeros you can easily see 1 0 is accepted, that is odd 0. This itself you can attack. But this says even zeros, not even ones, even zeros. Immediately make it accept odd zeros, finished. 1 0 is accepted, over, throw it out. Okay, understood. Choice B is what? Even ones and every one is followed by exactly 1 0. How do you attack choice B? Even ones. Even ones you can't attack because here you can attack this part exactly 1 0. Make it accept more than 1 0. For example, every one should be followed by exactly 1 0. See 1, 1 0, 2 0. It's accepted. That means 1 0 0 1 0 is accepted. This is a counterexample. This is a non-member. Instead of exactly 1 0, you have 2 zeros. Make it accept. 1 is followed by 2 zeros. Finished. Even if there is one non-member accepted, so this is gone. So this is also thrown out. This is thrown out because even 0 is accepting odd 0. What is left? This one. This is of course the answer. You can't, also one more thing is you can't find counterexample for this because it's a correct answer. Even ones. Notice every one, see 1 1 is followed by at least 1 0. More zeros are also okay. Here also 1, at least 1 0. More zeros are okay. But if the 1 is followed by 1 immediately, it's trapped because permanent reject, trap. Here also 1 is followed by immediately by 1. Immediately if two ones come together, gone, it's now hopeless, so trap. So this is a perfect design for this, D is the answer. So now you understand how this is very important, because this type of question has come many times and they expect you to be thorough with this counterexample method. Okay, understood. Of course, if it's a machine which you recognize already, directly you can take the answer, but in this case not a standard machine. Mostly they won't give standard machine, they will give variations. So you have to do it by counterexample. Okay. On one side you see how you will design it, on another side counterexample. You can see that this design is correct. Of course in the exam, once you throw these three out, finish, ticket, don't waste time. Okay. You have to do minimum things in the exam. But right now I have time, so I am going to tell you how to think about the problem. Okay. Let's now move forward. Question number 2. As I told you, the most important thing in TOC, in all of it, is regular expression. So let's immediately go to a regular expression question. Year after year regular expression question comes. Particularly this even odd number is very, very important. Even number of zeros, odd number, this type of thing, variations of that. Which of the following is a correct regular expression for all the strings on the alphabet on 0, 1 star? That means the alphabet is 0, 1. Regular expression on this. And what they are asking is for not containing substring 110. This is the question. Now before I write the answer, I want you to think about this. See, containing the substring 110 is easy. 0 plus 1 whole star, 110, 0 plus 1 whole star. But they are asking not containing. Negative things are not trivial. Okay, so you may have to go by counterexample method. That means take the answers one by one and try to generate a counterexample. Make it the regular expression either reject, not generate a member, or make it generate a non-member. Finished. Like that you can do. On one side also think how you can write an expression for this. Okay, both sides will think and will get the answer. A. Remember, these are rank determining questions, so it won't be trivial. You have to think. Each answer will look correct, but there will be something wrong with the wrong answers. Remember, these are multiple choice questions. So only one correct answer, so many wrong answers will be there, but they will all look right. Let's take this. Choice E. Choice B. 0 plus 1 whole star. This is 0 plus 1 whole star minus 0 plus 1 whole star, 110, 0 plus 1 whole star. 0 plus 1 whole star into 000, 001. 010, 011. 100, 101. 110 is not written, so 111 into 0 plus 1 whole star. This is answer B. It means they have written all the 3-bit strings, all the 7 of them except the 110. Okay. Next, 0 plus 10 whole star into 1 star. Then D. 0 plus 10 whole star followed by 0 star. Very similar answers, but slightly different. This is 1 star and this is 0 star, that's the only difference. Both are 0 plus 10 whole star. Now this is not a standard thing, it's a negative condition. So let's see. First, A. Immediately you should know that they are asking which of the following is a correct regular expression. This is not a regular expression at all. Although it is correct, but it is not a regular expression. Because after all, when you subtract 0 plus 1 whole star minus this, because this is containing the substring, when you subtract from the universal set, you are going to get not containing. But this is informal. They are asking which of the following is the correct regular expression. In regular expression, you are not allowed to use minus. Minus is not allowed. So this is incorrect. Even though it looks correct, it is incorrect. Next. This one looks correct because after all, other than 110, not containing means what? Don't allow the 110. But this is a trap. This is actually wrong. It looks correct, but it's wrong. Where is the mistake? You should realize that this part is 0 plus 1 whole star. Negative conditions you cannot do like this. See, for starting with, ending with, you can do like this. This method. That means if you want not starting with 110, you can make it start with all the other things. But even there you have to be careful. You have to accept 0 bit, null, 0, 1, 0, 0, 0, 1, 1, 0, 1. Because all the 0 bit, 1 bit, 2 bit will also satisfy not containing 110. Sorry, not starting with 110 or not ending with 110. So those are not here. They are all, minimum is all 3 bit. That's also wrong here. Understood? So even if it was starting with, ending with, you can still write it like this, but you have to make sure you also add all the 0 bit, 1 bit, 2 bit, all those things. But in containing the substring, not containing the substring 110, there is a problem already here itself. First of all, it doesn't have, because not containing the substring 110 should include null string. You can't create null string from this, first of all. That means the smallest member of this language, not containing 110, is null string. Null string doesn't contain 110. Your expression is not able to generate null string, finished, throw it out, counterexample. But there are other problems also. For example, this can easily create, using the 0 plus 1 whole star, I can create 110 from here. Even though 110 will not come here, it will come here, it will come here. So you can create things with 110, but you are saying not containing. So many reasons why this is wrong. That means this method will not work for the substring thing. Negative substring thing you can't do. You can use it maybe for not starting with, not ending with. You can use this method carefully. That is, provided you add the 0 bit, 1 bit and 2 bit strings. Then prevent this, say not starting with 110. Make it start with everything except 110. And then add all the 0 bit, 1 bit, 2 bit. It will work correct. But here it won't work in substring. Okay, then here. Let's come to 0 plus 10 whole star, 1 star. What is this correct? Again, let's start with simple counterexample. Okay. For example, let's see 0 plus 1 whole star. What is the smallest string which satisfies this? Null string. Yes, null string will come. This also will come, this also will come. Correct? Both will come. Only one of this is correct, is my MCQ. So we see null will come from both. Take the next member. Simple member will be what? Take the next 1 bit string, 0 and 1. Both 0 and 1 does not contain 110. Both are members. So whatever is the correct answer should create 0 and 1. Can this create 0? Yes, this also can create 0. So no. But can this create 1? This can create 1, but this can't create, because 1 is always followed by 0 here. Single 1 will not come. The single 1 is a member. Finished. So by using this minimal string method, we have thrown this out. So what is left this? Here you can't find any counterexample. In fact, you can also see, try to create something with 110. You can't. This won't allow. Here also it won't allow. 110 you can't get. You can get 1010, not 110. Here also you can't get 110. So therefore, this is indeed correct answer. Okay. So by counterexample method we have thrown out. But actually, if you want, you can even derive this directly also. How? Because you can use the machine and derive it. I'll just show you. Although in the exam don't do this, but just to tell you that this is not some. You may be wondering, how do I know that this is correct? Just because we are not able to find counterexample, can we say it's correct? Yes, in the exam you can say. But rigorously, if you want to show it, you can. I'll show you rigorously. How? Not containing the substring 1. In some cases, you can go to the machine and get it. In simple cases. For example, containing the substring 10. How do you design the machine for this? Containing the substring 110 is 110. Then put it accept, permanent accept. Substring machine is permanent accept. No trap. Now put the remaining things, because we want a DFA for this. So let's finish the things. Okay, because we want not containing means, because in NFA you cannot do negation. The complementary machine doesn't accept complementary language. So you have to use a DFA, you can't use NFA. Okay, so you will have to see, first let's do containing the substring 110, the DFA for it. So what will happen to 0 here? No progress, so keep it here. Here 1. If a 0 comes, we want 1 and 1 together, so 0 should be pushed back. Here 1 already is 1 1 containing 1 1, now also it's containing 1 1. So this is the design for containing the substring 110. So not containing the substring 110 will be just a complement of that. Now this looks very complicated, but actually you can easily write it. You can write the regular expression and you will get exactly this. I'll show you how. Let's first write, because there are three states, A, B and C. Let's first write A and write all this as a function of A. Whenever you have sequential things, that's how you write it. What is the A? 0 plus 10 whole star. A is 0 plus 10 whole star into null. Why I am writing into null? Into null will give A. Now B is nothing, this state is nothing but whatever comes here followed by 1 will come here. So plus 1. This followed by 1. A into null is A into 1 is B. And what comes to C? Let's call this as A, B and C. What comes to C? Whatever comes to A followed by 1, 1 comes here. Sorry, 1, 1, 1 star comes here. So 1, 1, 1 star. So C can be written as a function of A. How? Whatever comes to A followed by 1, 1, 1 star. No one it takes because it's already taken in A. This loop also has been taken in A. So just go to A followed by 1, 1, 1, 1 star comes to C. So A plus A followed by 1 plus A followed by 1, 1, 1 star. Now you can use the properties of regular expression and simplify it. How? What is null plus 1 plus? This is 0, 1, 1, 1, 2 or more ones. That's everything. So it's 1 star. That is what this is. 0 plus 1, 0 whole star into 1 star. So you see, even this strange expression actually can be derived. But in the exam, don't waste time like this. I am just showing you that in case in the exam they ask you to write regular expression for this, they give a machine instead of language. Now you know you can use properties of regular expression and do it. If you want, you will get this answer. Okay. Anyway. So, but by counterexample method, anyway, we have found that there is no counterexample for this. And these three are thrown out, the answer is clear. Okay. So, that is question number 2. Now, let us move to the discussion of the next question. Question number 3. So, while doing each questions, you will be getting multiple concepts. You have to apply multiple concepts. Mostly the rank determining questions are like that. You have to apply multiple concepts while solving the questions. That means you have to put together, synthesize many things you have learned here and there, you have to put it together on the spot. And these are the 2 marks questions, and these are the ones which very often determine the rank. Usually people who are somewhat ill prepared, they won't be able to answer this. So make sure that you are well prepared and alert. Okay. Because these rank determining questions, the main thing is that the rank determining questions, every answer will look correct. So many people will take wrong answers, but you don't take the wrong answer. Okay. Let's move forward. Question number 3. Third question we will discuss. See, sometimes they do ask you to count strings of certain type. You should know how to do that. In the exam, sometimes questions have come even in PDA. They give the language and they ask you how many strings are there accepted by this PDA of a certain length. So for practicing that, I am giving this question. This particularly comes in numerical data type. Okay. Let n100, counting problems are very good for numerical data type. Let n100L represent the number of this type of strange terminology. They will always in the GATE they will define it. Let this represent the number of bit strings of length exactly 100. That is 100 length strings. They are calling n100L as the number of bit strings of length exactly 100 in the language L. They have defined it. Now they are asking which of the following languages satisfies log 2 to the base, log to the base 2 of n100L is equal to 50. Okay. So they want to know which of the following languages satisfies this. Log to the base 2 of n100L should be 50. Or you can read this as, what does this mean? You can read this as n100L should be equal to 2 power, that means the count. How many 100-bit strings are there, exactly 100-bit strings are there in the language, should be 2 power 50. Which is that language? That's the question. Whenever log is given, you can invert it, it's easier because we have to find, we can find n100L easily. How many 100-bit strings are there? That's we know. So we want to find which n100L is 2 power 50. Let's see the answers. A. So you try this question. A plus B whole star B. Then A star AB into A plus B whole star. Then AA plus BB whole star. D, none of these. Okay. Now you try this. Which is the answer? Try it. It means in each case you have to count how many strings are there in the language which have a length of exactly 100 bits. How do you do this? Which one and which one will come to 2 power 50 we have to see. So in this case we cannot directly get the answer. You have to do one by one. Numerical data. Not numerical data. In this case, it is like numerical data. They could have asked how many, but instead they have asked like this. It becomes multiple choice question. It's not numerical data, it's MCQ. But this could come as numerical data type also. Only thing is number is a bit big, 2 power 50. But anyway, they could ask log is, they can ask you what is this log equal to. Okay. And they can give this language. But in this case, you have to do 4. So this will be clearly a 2-mark question. Let's see one by one. How many 100-bit strings are there in this? How to count it? Easy. This is fixed already, 2 bits are already fixed, you can't change it. Every string you generate from here will have A here and B here. So remaining how many bits should be coming from here? 98 bits. Totally 100 bits, right? 98 bits, each of them, there's no choice, this will be A and this will be B, so don't count it, forced. But here it's not forced. Those 98 bits you can choose either A or B. How many ways can you do it? Each bit can be chosen in 2 ways, so 2 into 2 into 2, 98 times, that will be 2 power 98. That means here, for this language, the N100L is 2 to the power 98. So clearly this is not the one. We want 2 power 50. So this is not the answer. Similarly, try this. Is this the answer? How will you do this? How will you count how many strings of length 100 are there? These 2 bits are forced. Here you have choice, but what choice do you have here? You can only put null, A, double A, triple A. Each of them will be different string. So let's do it systematically. Let's put first null, starting with null. When you put null, you will have AB into A plus B whole star. How many strings of this type of them? It starts with AB. That means we put this as null, it will start with AB. How many strings of this type? 2 bits are fixed, the remaining 98. So this will be 2 power 98. That will be 2 power 98 strings like this. Now let's put this A star as A. Then you will get AAB into A plus B whole star. Now 3 bits are fixed, the remaining will be 2 power 97. Such strings. Next you take AAAB into A plus B whole star. Now 4 bits are fixed, so remaining will be 2 power 96. You can see the system here and so on. Eventually you will come to a point where this you take all the 100 bits here only. That means take 99 A's followed by B and this will become null. That will be 2 power 0. That means don't take this at all. Just take all of this here. That means take all the 100 bits from here only, take this null. That's 2 power 0. Now you add all this because there are so many strings of this type, add everything. So what will you get? Start from the bottom. 2 power 0 is 1. Next will be 2 power 1, 2 square, etc. up to 2 power 98. 2 power 96, 97, 98 like this. I am doing backward counting. So this is geometric progression. A starting to A into R power, number of terms is 99. 98, this is 0, 2 power 0. 0 to 98, 99 terms divided by 1. A into R power n minus 1 by R minus 1. 2 minus 1 is 1. So this will be 2 power 99 minus 1. So therefore the answer to this is N100L of this is 2 power 99 minus 1. So this is not the answer. We want 2 power 50. So this is not it. So it has to be either this or none of these. Let's check this. AA plus BB whole star. What is AA plus BB whole star? AA plus BB whole star, how to do it? Here always you will take 2 bits only. Whatever you do, it will be double bit. So instead of counting 100 bit strings, let's count 50, because if you take any 100 bit string, it can be broken down into 50 pieces. Each of this is either AA or BB. Each of this like this. If you take 50 such things, each of this is double bit, you will get 100 bits. So how many 100 bit strings are there? Each of this double bit can be either AA or BB. I can choose. So there are 50 spaces, each can be filled in 2 ways. This can be AA or BB, AA or BB, AA or BB. So 2 into 2 into 2, 50 times. So it will be 2 power 50. This is the answer. This is the one. So here the L100 is exactly 2 power 50. So therefore the log of N100L, the base 2 will be 50. So this is the answer, C. So answer is choice C. Okay. Understood. Anyway, the answer to question number 1 was D. Answer to question number 2 was what not containing the substring 110. Okay. So that it was C. 0 plus 10 whole star 1 star. C. So 1 was D and 2 was C and 3 is also C. Okay. So like this we'll keep doing questions and we'll discuss each question so that you get the strategy. The important thing is not just getting the answer but the strategy. How to think, because this type of problem comes very often. Okay. So this is question number 3. Now we'll come to question number 4. Question number 4. What do we have here? Which of the following regular expression does not generate the language, which language? The language odd number of B's. Remember, this odd, even, mod things are very important for the exam. Do as many questions as possible in regular expressions, machines, and all these things for odd, even, this type of things. It keeps coming again and again because there are so many variations. In this case, they are given. This is a standard question, odd number of B's. But the answer may not be so standard, so you have to see. Let's see how it is. Remember, there are so many answers for odd number of A's, odd number of B's, even number of A's, even number of B's. You have to be totally thorough with every way because they can give any of those things. Okay, B, A star, B A star B, whole star, and then again A star, B A star. And choice C is given as A plus B A star B whole star, B A star. And D is given as A star B into A star B A star B A star whole star plus A star. We want odd number of B's. First of all, do such question, you must know all the standard ways of writing it. So how will you go about odd number of B's? See, you see here all of this has B A star, either A star B or B A star. That means B A star means this is the last B. A star B means this is the first B. This you have to be fluent. To make your work easier, first get rid of this B A star. Because once you get rid of the last B, whatever is left should be even number. Because even number followed by B A star or A star B followed by even number will be odd number. So you can just, to make your life easier, just get rid of this. Get rid of this. It will make your discussion more easy. Now all you have to do is check whether whatever is left should be even number of A's. So even number of B's. Because one B is taken out, the last B. Understood? This has to be even number. Now your problem reduced to which of the following is the even number of B's. Let's see this one. Is it even number of B's? Even number of B's, how do we write it? So many ways that write it. Is this one correct way? Yes, it is a correct way because you can see two B's inside the star. Even means you have to break it down to two B's. Two B's normally we write A star B, A star B, A star whole star. Okay. That's how we write. Plus A star. But since this plus A star is not there, you have to create the A star also here. So what they have done, you can do dot A star also. Either you can do plus or dot, both works. You know this method, right? Because by putting this null, you can get this only A star. By putting this null, you will get this. Okay, by using both, nothing new will be generated because this A star is already here. This A star will cost nothing new. A star and A star is A star only. So therefore, it's able to create. But here what they have done, this A star is redundant. It's not required at all. That's what they have removed here. See here. A star, this A star has been removed. This is also still correct. B A star, this one. B A star, B A star, whole star. So this part indeed is even number. Why this A star is redundant? Because this A star, whatever the work this A star can do, that is bringing the A star in the front. That this will do anyway. Why do you need this A star? You can argue that in between this you may want A, that can be done by this also. You don't need this A star. One of these A star should be present. If you put A star here, you can remove this A star. Or if you put the A star here, you can remove this A star. No harm will come. So this is correct, clearly. Okay. So we want does not generate. So this is not the answer. This does generate. So this is actually odd number of B's. We want something that does not generate odd number of B's. So here A is not the answer because it does generate odd number of B's. What about this? Here notice what they have done. Is this creating what? Even number of B's. Notice here this side also A star is removed. This side also A star is removed. Okay. This is not correct. In fact, this is the answer. This does not generate. This is the answer because this is not odd B's. Why? It is incomplete. It cannot generate. Why? I told you, you can't remove A star from both sides. If you put a star here, you can remove this A star. But you cannot remove on both sides. If you do that, what will be wrong? Is now you cannot create, let's say you want to BAB, just take a simple example, BAB, put another BAB and put some A's in between. These A's will not come. You either need a star here or a star here. So this particular string has even number of B's, BAB, AA, BAB. You can never get it from here. Understood? Because here also A star is not there. So between the two BABs, BAB is there, but you want to put two AAs in between BAB. There is no way to put that. In between the two B you can put, in between two BAB you cannot put. So therefore this is incorrect. That means you can't remove A star from both. Either you remove from this side or this side. Can't remove from both. So this is the answer. But how is this correct? Is this, we have not studied this at all. A plus B A star B whole star, does it work? Here notice this side also A is removed, this side also A is removed. This is correct because you have put this plus, it's not outside. It's inside the bracket you have put A plus. This will create. Because now in between BAB you can put any number of A. You can take any BAB and put any number of A, this side also, that side also, in between also. And it will create A star also. So this is correct. But this can be proved correct in another way also. Instead of just proving it logically, I can prove it through machine also. Remember, for things like even and odd, you can even generate the, remember also the expression which comes from the machine. Normally you don't have to remember regular expression coming from machines. Because usually machine expressions are very complicated. But even odd is so simple, it's a good idea to remember it. See, for example, even A's, what is the thing machine? This is even A. Sorry, we want even B, sorry. We want even B. This is the expression for even B. This is the machine for even B. What will be the expression? A plus B A star B whole star. A plus B A star B whole star. That's what they have done here. A plus B A star B whole star. So it's a good idea to remember that A plus B A star B whole star is actually a technique for creating even number of B's. Similarly, if you want even number of A's, it will be what? B plus A B star A whole star. It will create even number of A's. So remember this. Of course, followed by B A star will give odd number, because if you make this, it will be this followed by B A star. Odd number of B's. So this is correct actually. So therefore we want not generate, this will generate. So this is odd number of B's. This of course is straightforward. This, once you remove A star B, this is even number of, this is standard one. This one what we wrote. A star B, A star B, A star whole star. Nothing has been removed, it's perfectly fine. This will create all the things multiples of 2. But the 0, this is created by this, A star. A star contains 0 B, 0 is an even number. So A star plus A star B, A star B, A star whole star. So this is also correct, odd B's. So the answer is choice B. So these are the first 4 questions. Okay. Now we will go to the question number 5. This question is NFA to minimal DFA. No, regular expression to minimal DFA. What is the regular expression given here? Consider the regular expression given below. 1, 1, 1 star, 0, 0 star. The question is the number of states in minimal DFA for this regular expression is what? The question numerical is what? Numerical data type. So let's do this. What are the guidelines when you convert a regular expression to minimal DFA? First, always try to simplify the expression if possible. Here this is 1, 1 star, 0 star, you can't simplify it. That's it. You can't simplify it further. So now what do you do? Try to make first the NFA, try to make a dead NFA which you can convert it to a DFA. Okay. But when you do that, try to make a minimal dead NFA, not just any NFA. So you should try to minimize the states as much as possible. Let's first do first step. 1, just follow the expression. 1 star means put a loop, a cycle. 1, 1, 1 star, follow it with 0, 0 star. But now you will find it difficult, because if you put 0, 0 star like this will become 1, 1 plus 0, 0 whole star. But if you want A star, B star. But then you have to put a null move here. 1, 1, 1 star, null, 0, 0 star. But then null move NFAs are difficult to convert, so we don't want null move. So let's rewrite the regular expression. 1, 1, 1 star. Write the second star, whenever you have A star, B star, write the second part as R star as null plus RR star. So this is 0, 0 star, null plus 0, 0, 0, 0 star. And now separate it out. Now the null move will go away. Otherwise, you can't apply algorithm. Null move removal algorithm don't apply. We don't have time like that. That's it. Now do it. Now what happens? Let's see what happens now. Now we have done up till here 1 1 1 star. Now there is no null move. This is 1 1 1 star. This is one fine state. This will be another fine state. 0 0 followed by a loop. 0 0 star. Finished. But this is not really a minimal NFA, because we can see this 1 is coming in here, also 1 is coming in. Maybe we can reuse this by putting a loop backwards. So whenever possible, you have to try to simplify it further. This thing, I can put it backwards. 1 1 1 star. Why I have to use this state? Now I have reduced one state. Here also same concept. 0 0 is coming here, 0 0 is coming here. So what you can do instead, just put it like this and put a loop. Just put a loop here. 0 0 0 0 star. Finished. Why you have this state? So this state gone, this state gone. Now you have a minimal NFA. Make sure it's a dead NFA. How do you check it? 1 there's no choice. Here 1 0 0 1 is dead. Here 0 is dead. Here 1 is dead. No choice anywhere. It is a dead NFA. So put a trap state and put all the dead arrows to that 0. Here 0 1 over. Here 0 is there. 1 will go to here. Here 1 is dead. So put it here. Finished. Now we have a minimal DFA. Answer is 5 states. Typical question. Okay. It's also a pending question because so many questions have come in direct FA design, but from regular expression design few have come. So this is pending. Good chance it may come, this type of question. But be alert when you have A star, B star, first do this. And also this looping. Whenever loop comes, try to put a backward loop rather than put separately. Okay, so that's question 5. Now let's go to question number 6. I have chosen questions which are likely to come, okay, and also slightly which involve some tricks. These are all rank determining questions where people can make mistakes. Because the straightforward questions you already know how to do. We have done enough in class. Okay, the ones where you have to be a bit careful, just last minute alertness. Those type of questions only I have selected here for doing today. Okay. Now let us do question number, so there was question number 5. Now let's do question number 6. Remember, closure comes very often. In recent exams, a lot of questions have come in closure. Closure questions are coming way too often. In recent exams, there are many closure questions. So be alert. And closure, I will talk about the common mistakes, silly mistakes that people make, and that is where the questions will be addressed. You are not supposed to make silly mistakes. 6 is a closure question. Which of the following is false? Which of the following is false? It's given that if L1, L2, L3, ... infinite number of them, is a countably infinite collection of regular languages. On some alphabet sigma, all of them are on the same alphabet, some sigma. Now, false. Which of the following is true? And there is an MSQ. I am keeping it MSQ because very often closure questions are MSQ. Okay. MSQ does not mean that there are multiple answers, but there could be more than one answer. Basically, that's the meaning of MSQ. It could still behave like an MCQ sometimes, but MSQ, more than one answers are possible. More than one can be true, basically. Which of the following is true? So let's see, what is A is given L1 union L2 union L3 ... infinite is non-regular. Next is L1 intersection L2 intersection L3, again infinite, is regular. And third is L1 union L2 union L3, the same one. Only thing now they are given, it's a CFL. Last is L1 union L1 bar intersection L2 union L2 bar and so on. Infinite is regular. So more than one answer is possible because it's MSQ. Try it. Try this, let me see. It's countably infinite collection of regular languages. Which are true? Just try this. How will you go about? First of all, you should know the closure properties of regular language. Regular language is closed in all things except subset, superset, infinite union, infinite interaction, infinite difference. Infinite union, infinite interaction, be careful. It is not closed. So therefore, this thing, they are all regular, but it's infinite. The fact that it's countable doesn't mean anything. It's infinite. It is in infinite union, it's not closed. So not closed, some people think that it means never. That means always it's non-regular. That's not true. So this is based on the common misunderstanding. Not closed means may or may not. So the correct thing is this union may be regular, may be non-regular. We don't know. So, but here it says it's non-regular. And this is just some arbitrary language. They have not given any specific language, so we cannot strengthen it further. If they have given specific language, maybe you can actually do the actual union and strengthen it further. Here you can't. So it's non-regular is clearly false. Here, even if they say regular, that also will be false. Only thing will be if they say may be regular, true. Okay. Here, interaction is regular. Again, infinite interaction also is not closed. Not closed means what? May be regular, may not be regular. They are saying it's regular, false. If they say non-regular, that's also false. Only correct answer is may be. Is a CFL. This is a temptation. You may be thinking, okay, it may or may not be non-regular, may or may not be regular. Surely it will be a CFL, no? No, that's not correct. No language is closed under infinite union. Even CFLs are, after all, a regular is a CFL, but even CFLs are not closed under infinite union. The infinite union of CFL can go outside CFL. It can be inside also. No comment can be made for this also. No language is closed. So this is also false. So till now we have not got any answer. But what about this? Here you have to be careful. Here it's the L. It's not just anything L1 union L2 bar. It's the L1 union L1 bar. So you can simplify it. In closure, always whenever possible simplify it. Otherwise you will get weak answer. Don't put regular union regular bar. No. You will get weak answer. Here, because then you will get regular and regular bar is regular, interest regular. Again you will say this regular is false. No, it's actually true. This one is true. Why? Because you can simplify it. This is not just any. This is the L1 union L1 bar is a very special language called sigma star. In fact, L union L bar is always sigma star. Since all are on the same alphabet, this is also sigma star. L2 union L2 bar sigma star. So A interaction, even infinite number of times only A. This will be equal to sigma star. So in this case, it becomes a special language, not just any random language. It is regular. It's true. Here don't say may or may not be. Strong answer is that it is regular. True. So what is the answer? D. Even though it's MSQ, the answer is only D. Okay. So this is question number 6. I am doing this because after doing all the things, many people still make mistakes. When they say not closed, people say never. No. Not closed means may or may not. Okay. Just remember that because I have seen people making this mistake all the time. Okay. 6 is over. Now we come to question number 7. Question number 7 is purposely I have kept it tricky because I feel that pumping lemma, because it's given explicitly in the syllabus and because only one question has come in pumping length till now. So I want to discuss it further. It's a pending question basically because very few questions have come here and it's there in syllabus. There's a good chance they may be tempted to ask it because they already asked it once a few years ago. Question came in pumping length, not minimum pumping length. Minimum pumping length is yet to be asked. So minimum pumping length also I am focusing on that. Of course, once you get the minimum pumping length, you can get the pumping length easily. Okay? Understood? So this question will be on MPL, minimum pumping length. I am addressing certain concerns because pumping length is a very tricky concept. If you don't understand this question, don't bother. It's not so important. But if it comes, it will become important because many people will make mistakes. It's just one question. So, but anyway, there is some chance. So, question number 7 is minimum pumping length question. So, I am giving the question like this. In the exam, you will get only one language and they will be asked what is an MPL or PL. Once you find MPL, you can easily find PL. PL is greater than or equal to MPL. So, minimum pumping length. But since I have time here, I want to discuss it a bit. Because I want to ensure that in case it comes, you don't make silly mistake. Okay. You have to know these actually. These 1, 2, 3, 4. The 5, 6, 7 is a bit tricky. If you want, you can omit it. But I'll do it anyway in case it comes. I don't want you to be perfect with this. That's why. Up till here you should know. The 5, 6, 7 starts becoming tricky. But I am giving it because they could ask and it will become rank determining. It will be surely a 2-mark question if it comes. In fact, the union of these two came in the exam, but separately it has not come. And even the union, very few people would have done it. It's a tough question, and also it's prone to error. I have seen even in the website, even now, wrong answers are given for this. So that's why I have to discuss it. I don't want you to fall victim to this. These brackets are there, I am not putting it back anyway. Okay. The union of these two came in the exam. Not MPL but PL, but to do the PL you have to first of all do MPL anyway. Once you get MPL, PL is very easy. So MPL, we are going to find minimum pumping length. Answers are given like this. You have to match the following. It is match the following. That means you have to do so many. Of course in the exam you won't get so many. You may get one or two. A few you will get 3 or 4, something like this, or just one you may get, depending on how tough the question is. D5. Different answers are there, you have to match it. Basically you have to find the MPL for each of this. Okay, now let's start one by one. But before we do this, I want to tighten out what you already know, because pumping lemma and minimum pumping length and the minimum pumping length are the most tricky concepts in TOC by far. Okay, what is the thing? First of all, what is exactly is the pumping length? Because MPL, minimum pumping length, is at least equal to pumping length. Sorry, pumping length is at least equal to minimum pumping length always. The pumping length is always at least equal to minimum pumping length. So once you find this thing, pumping length is not unique for us. Minimum pumping length. Once you find MPL, pumping length is any number at or equal to MPL. That's all. So PL is not very important. This MPL is important. It's the minimum pumping length. Okay, so these are concepts. What are the concepts that you know? MPL has to be at least equal to 1, because you cannot pump a null string. Okay, the pumped bit has to be at least 1 bit, so it can never be 0. So MPL is at least equal to 1. Now what are the other things that, let me just list out the things that you have to know about MPL, okay, and then we can proceed forward. The things that you have to know. Okay, next, MPL must be at least equal to the number of states in the minimal DFA. So at most, this is at most. This puts an upper limit. It cannot be more than the number of states in minimal DFA. This is not so useful and you won't use it much. But in cases like, for example, even number of A's, you should know that even number of A's, there is a minimal DFA with only 2 states. When the number of states for the minimal DFA is very small, it's useful. So it means you cannot go more than 2, and it has to be more than 1, so it has to be 1 or 2. For even number of A's, it has to be 1 or 2. Similarly, in case you have it will be at least n minus 1, where n is the number of states in minimal DFA. Here it's n minus 1, where n is the number of states in the minimal DFA. When it is n minus 1, in case your minimal DFA has a trap minimal DFA. Here, in case there is no trap, just take it as less than or equal to n. But only the upper limit can be strengthened. In case you have a trap, just remove the trap, make it n minus 1. Don't count the trap in this type of thing. Okay, but this is not all that useful. It only puts an upper limit. This puts a lower limit. So between 1 and this, always MPL for every language between 1 and this. This is a strong compared with this. This you can use it only in case there is a trap. Just don't go. Here n is the total number of states minus the trap state. You can put a limit like that. Next, MPL is more than the W minimum. That means it can never be less than the minimal string in the language. In any language there will be a minimal string. Even in infinite language there will be a minimal string. Always identify the minimal string. Remember, you can't go, it has to be at least 1 above that. Up to minimum string the answer will never come. That means it's at least equal to, another way of writing is at least equal to minimum string plus 1. Because greater than minimum. Why it cannot be up to minimal string? Because up to minimal string you cannot pump at all. If you pump the minimal string, remember the pumped bit can go up to, you can repeat it 0 times. X, Y, Z is pumped. Y power 0 will make it XZ. That means the pumped bit may vanish. And the pump bit is at least 1 bit. So in case the pumping length is anything at or less than the minimal string, you will get the minimal string itself will get changed. Because now the pump down, when you pump it down by putting y power 0, the something smaller than the minimal string will start belonging to the language, then that means it's a contradiction. So that is why at least, so that means for example here the minimum string is 3, your pumping length has to be at least 4. Here it's null, pumping length is at least equal to 1, here at least 4. So the minimum, this is very, very important. Always identify the minimal string. You can't have it less than the minimal string or even equal to the minimal string. It has to be one more than the minimal string. This is the first thing you always use, first one. Okay, and this of course trivial, it cannot be 0. These two are the most important thing. It has to be at least 1 and it has to be, make sure find the minimum string. This will of course be usually stronger than this always. Then next, in case it's a finite language, in the case of finite language, what we can say, MPL at least equal to W max plus 1. Now the maximum string will control. Here the minimum string will control in infinite language. In finite language this will be bigger than this, so you use this. In fact in this case not even greater than, it's equal to, exactly equal to. In the case of finite language the answer is trivial. Take the bigger string, add 1 to it, you get the answer. You don't even have to search further. It's exactly equal to, here it's at least equal to, here exactly equal to. The reason is because up to maximum string you cannot pump at all. The moment you pump any string in the language, in a finite language, it will become an infinite language. So it means basically you should take such a number where the string itself doesn't exist. What is that number? Take the bigger string plus 1. Then trivially no string will exist at this, so you can pump. That means if it is there you can pump it, but there will be nothing. Basically in a finite language you can't pump any string because the moment you pump a string it becomes infinite language. So trivial answer for finite language. Then what else you have to know? Pumping length is always greater than or equal to MPL. That's what we wrote here anyway, that's over. Once you get MPL, you take any number can serve as a pumping length is not unique for a language. Any number at or above MPL will serve as a pumping length. Okay. So that's it. These are all the things. Now the only tricky part which will come here, starting from here, I am going to use it, starting from here itself, which many people are making mistake is because there is one more theorem here which you have to know. What is that? This comes based on the fact, this comes based on the formal definition of pumping lemma. Many people are not aware of this. That means the pumping length has to be at least equal to the pumped part, which I will call it as Y. See this part which you are putting a star right here, 1 star. This part, this pumped part, this is a Y. This part, your pumping length has to be at least equal to that. It cannot be less than that. At least equal to that length. The length of that Y, the pumped part. This many people are ignoring it and that's why wrong answers are coming. This is the one I am going to focus on today because all the others you know already. In the class we have done everything. But this one, even in the class there was a mistake based on this, so just watch out for this. It's a very tricky one. In many websites they are not considering this and it's wrong. It has to be considered. It is part of the pumping lemma. I will tell you where this comes from. This comes from the formal definition of pumping lemma. Pumping lemma, the informal thing is what? If the pumping length is say P, we say that if a language L is regular, there exists some P, an integer, such that, what we say? There exists some P at least equal to 1 because pumping length has to be at least 1, it cannot be 0. And what we say, for every string W which belongs to L, whenever W is greater than or equal to this pumping length, every string at or above the pumping length, what we say? Then it can be pumped. That means what? Every string W which is at or above the pumping length, whatever belongs to the language, must be pumpable. Pumpable means what? This can be pumped. This is an informal. Exactly what is the meaning of it can be pumped? That I will show you now formally. This is the informal definition is every string at or above the pumping length must be pumped. Pumped means what? It must have some part which has a star on it. And the star can be taken 0 times also. That means you can pump it down or up. So that's the thing. So now I will write this formally. What do you mean by pumped? It means that such a W can be broken down into X, Y, Z. This X and Z can be null, but Y has to be at least equal to 1. That is obvious because the pumped part cannot be null bit. It's a non-null bit. And the tricky part is this one, and XY has to be less than or equal to P. This is the part many people are ignoring. That means the pumping length has to be at least equal to XY. See, I am not taking X because X can be put as null. X can go to null. So, but this Y cannot be put as null. So, you have to consider its length. That's why I am saying this comes from this. P at least equal to the length of Y. X can be put as null. In some case even X cannot be put as null, then you have to consider that also. For example, this one X cannot be put null because X is non-null. I will show you there is a difference. So, that also will come, but in general this is strict one. That means in every language this has to be. Because in whatever X can be put as null, Y can never be put as null. So, Y has to be at least equal to the pumped part. Here Y is the pumped part, this starred part, this length of this 0, 1, length of 0, 1 is 2, length of this 1 is 1, this length is 2, it cannot be less than that. So, this is the only thing that we are going to add today, okay, and make sure this, okay. Now, we are ready to do this question. This question will illustrate all of these things. Using this question I can illustrate all of these things. Now let's do this question one by one. Now we are ready. So just add this to your theorems. Okay, this one last one. Pumping length cannot be less than that pumped part. Okay. Okay, now let's do this. First, this is the easy one. First thing, what? Pumping we want minimum pump MPL. All of this is for minimum MPL only. MPL, what is this? Minimum string is 3. So you take at least 4, at least equal to 4. In this case, it's 4 itself because you add one bit. Fourth bit can be pumped, that's it. So answer is 4. So for A it is, for 1, 4 means what? C. 4 is the MPL. Okay. So match the following. 1 is matched with C. Now let's take 2. 0, 1 star. This is a tricky one. Many people are taking the answer as 1 for this. Actually it's 2. The answer is 2. Matched with A, 2. So the 2 answer is A. Why it is 2? It is because of that thing I told you that the pumped, this bracketed part, bracketed star, this has a length of 2. So your MPL has to be at least equal to 2. How can you have 1? Some people are taking it as 1 because they are arguing that any string of length 1 or more, which is here in the language, is pumpable. Yes, that's true. Because there is no string of length 1, so you can safely take it as 1, but you can't take it. In this case, you can't take it because you have null, of course, 0, 1, then 0, 1, 0, 1. These are the strings in this language. Null you cannot pump. Let's take 0, 1. Okay. Now, any string of that means the pumping length cannot be 0. It has to be 1 at least. But can it be 1? That's the question. Yes, there is no string of length 1. The 2, this is of course pumpable. But there is a problem here. This violates this thing because if you take it as 1, then you have to show that x, y, this thing less than or equal to p. And you are taking pumping length as 1. But this is 2. In this case, what will you take? If you take 0, 1, you can take the x as null, y as 0, 1 and z as null and pump this. Yes, you can. But now it will violate this condition because x, y, the total length is 2. 0 length plus 2 length. 2, this is false. 2 cannot be less than or equal to 1. That's why I said always make sure that in case you are getting, okay, 1, you are getting tempted to answer 1. Before you do that, you see the bracketed star, what is the length of this? This is 2. How can you have 1 as the answer? It is 2 actually. 2 is the answer. You have to make sure that the 2 is, now it's okay. Okay, 2, because now you can put pumping length as 2, now it's okay. So 2 or more, so in this case you can't take it as 1. Okay. So in the class there was an error in this, please correct it. Okay, the 0, 1 star is not 1 actually, it's 2. Similarly, if you have 0, 0, 1 star, again you may be tempted to give MPL of 1, it's not 1, it's 3. Because this starred part, this y, this is your y. This pumping length has to be at least equal to this y, at least 3. So 3 is okay. 3 or more, whatever is there is pumpable. So don't take it anything less than 3. Don't take it as 1, don't take it as 2. It's actually 3 for this. 0, 0, 1 star. Okay. So now you got it. Similarly 0, 0, 0 star also it's 3. It's not actually 1 or 2. Make sure you don't go less than this bracketed star part. The length of this controls. Okay. So 3. So this is 2 actually. Then here. You can't go here. Okay, this is 2. But you can't take 2 because the minimum string itself is 3. You can't remember. While doing one theorem, don't forget the other theorem. You have to go at least 4 here. So here can you take 4? That's the question. Can you take 4 here? If you take 4, what will happen? See, now you go. If you get this string, how will you pump it? You will take this as x. You have to take it as x. Because you can't take x as null. This part only can be pumped. You will take it as y. Now if you take it as 4, you have to satisfy this. If you take this as 4, but this is 5. How can 5 be less than or equal to 4? So here you have to take 3 plus 2, 5. So here it is 5, that is D. So this is D, that is 5. Okay. So 3 is D, that is 5. Don't take it as 1 here. Don't take it as 2 also because you have to take the minimum string plus 1 minimum. The MPL is at least equal to minimum string plus 1, so 4. But even 4 you cannot take because you have to take this part fully to pump. So 5, it is 5. Okay. Whereas when we come here, it becomes a tricky. Starting from 4, it becomes a bit tricky because this thing, although it's like this, you may be tempted to say 3 plus 2, 5. But you can shift it this side. You can rewrite it like this and make this as Z. Make this as Y. X, you take it as null. Now you can even 3 will work. Why should you go for 5? Because you can shift it here, you can't shift it here, you cannot write 0 0 0 0 1 star, this side you cannot write it, the other side you cannot write it. Okay, so this is actually, what is this? This fourth one, 4 is going to C, that is 4. Here you can take it. Why I am taking 4? Because even though it is like this, 0 0 star, I can rewrite it, I can take it x, y, z like this, but I have to respect the fact that the minimum string is 3. So I will be tempted to take, okay, 2, I will be tempted to take the answer as 2 because I can shift it, but that will violate the other theorem. Minimum string is 3, but in this case I don't have to take 5, I can take 4. I can take 4, minimum string plus 1, 4, and there is no 4-bit string here, I am safe. 4-bit string is not there, so I am safe. And I am still safe with this also, because x, y, z I can rewrite. If you get, for example, 5 zeros, I can bump it like this. I can bump this part, keep it as z. That way I have no problem, because now you see my pumping like this 4 is, this 2 is less than or equal to 4 is still satisfied. Understood? But this we could not do here. That's why, understood? That's why it is 5, whereas here it is 4. You have to understand why this is 4 here. Okay, it cannot be anything less than 3 because minimum string is like that. Similarly, now we can do this. Okay, let's finish this off. Now the tricky part is understood. The others are easy. A power 2 plus 3k is nothing but AA into AA star, same as this basically. Same idea, only thing is 2 and 3 star, this is 3 and 2 star, that's all. Same idea, what will it be answer here? It has to be 1 above the minimum string. So try to get away with 3 because there is no 3-bit string here. But further, can you push it this side? Yes, you can rewrite this like this if you want. So 3 will work because you can take the x null, take this 3-bit and pump it. So 3 will work here. So 5 is what? Okay, 3, because the pumped part 3, right? You can't go anything less than 3. Okay, so 3 is the answer here. And you have to go one more than 2 because 2, the minimum string is 2. 3 will work here. So answer is, what is this? 5 is B, that is 3. Okay. Similarly, 6 you can do B power 10, 12k. Same idea here also. You have to go one above the minimum string that you cannot escape. So 11-bit string is not there. But can you get away with 11? That's the question. 11-bit string, there is no 11-bit string here. Okay. So can you get away with 11? The answer is in this case is, you just see here, 11. The minimum thing here, this pumped part, see you have to go one above 10, but the pumped part, A, B power 12 star, remember this is your y always. You can't go less than this part either, you cannot go less than y. So you can't go with 11, even though there is no 11-bit string, but you can't go because that other thing I told you, right? MPL has to be at least equal to y. The y here is 12. You can't go anything less than 12. You can't go anything even 10 or less. So you can't go 11 also because 11 is less than 12. So you can take it as what? 12 itself. So you can take it as 12. So here it is F is 12. Here it is 12. But this one, the last one, you won't be able to shift it this side. So this 10 you have to take plus 12 also you have to take, it will become 22. So 22 means what? So G is 22. By mistake I wrote 12 here. So this is F and then this is M is G. That is 22. So here it is 22. G will be 22. Why 22? Because you have to go one above the 10. Minimum string is 10. A power 10, B power 12k. So minimum is 10, so 11 you have to go. But in this case you can't shift the pumping on the front. You have to take this, that means you have to take 10 A's and then pump this 12k. And you can't go less than 12 also. Okay, you have to take this 10, you can't shift it, that's it. So minimum X itself will be this 10. Y you have to take the whole thing B power 12. So 10 plus 12, 22. You can't, because P should be at least equal to XY. And here the XY length is coming 10 plus 12. You can't shift it this side because this is A and that is B. So answer is 22. So this is the most tricky one. Okay, I just did this thing just to protect you, that's all, but don't bother. If you don't understand this part, leave it, it's not very important. Okay, but for those people who want to get top ranks, they have to know this much. Okay, so this is a slightly tougher question. Okay, question number 8. So here you are given a context-free grammar. Consider the following CFG and what is the grammar given? It is given S goes to S1, S2, S3. Clearly the language will have three parts if you solve it, which will be in union. And the first one is given, this one. You should immediately know that this is a standard grammar. You should be familiar with all the standard CFGs. This is another standard CFG. And this one is a simple substitution. A is not in recursion. Just substitute A, whatever A is. A is a simple regular grammar. Sometimes a CFG can have a regular part. This is a regular grammar. So just you have to solve it and then you can answer which of the following is true. Which of the following is true regarding LG. The question is regarding LG. So you have to solve LG. First, LG is a DCFL. Of course, because it's a CFG, you know it's a CFL. CFG will only output a CFL. But is it a DCFL? So you have to solve it. If they say LG is a CFL, then no need to solve it. You know it is a CFL. CFG will only output a CFL. Next, they are also asking what is LG. So again you have to solve it. LG is equal to A power M, B power N, M not equal to N. 3. LG is complement of A power N, B power N, N greater than or equal to 0. They are saying LG is a complement of this. And 4. LG is CFL but not a DCFL. Just try this. Solve it and tell me what it is. Remember, CFG solutions are very important for the exam. Very often questions come. So here, we have now finished with all the things in chapter 1. We are coming to chapter 2. CFGs. Typical question in this. Which is the answer? Here. 1, 2, 3, 4. And the answers are given in A, B, C, D form like this. What are the answers given here? 1 and 2 only. 1 and 2 only. Then 1 and 3 only. Next is 2 and 4 only. And last is 4 only. 4 only. Okay. So try this question. What will it come? The correct answer, let's see how to go about with this thing. The correct answer happens to be 1 and 3. 1 and 3 only. They are true. Why? Let's solve it. S1. See, if you put S goes to S, this will create equal number of A and B, but if you put null, it will become equal number, but you are putting A S1, it will insert some extra A's. And we know at least one A will get inserted because this A is not null. If this was null, it will become A power M, B power N, M is greater than or equal to N. But now it will be strictly greater than N. So solution of S1, L of S1 will be simply A power M, B power N, M greater than N strictly. So at least one A will get inserted. Here B is inserted on the right side, and if it was null, it would have been M less than or equal to N. But now it will be M strictly less than N because at least one B is getting a. So LS2 will be A power M, B power N, M less than N, or in other words N greater than M. B is strictly one more than A. These both are standard grammars. This one you can just do by substitution. This is what? A plus B. A goes to A plus B whole star. Just substitute it here. A plus B whole star, A plus B whole star. This is L of S3. Now put it all together. S1, S2, S3. It will be what? A power M, B power N, M greater than N, union A power M, B power N, M less than N, union some regular expression A plus B whole star, A plus B whole star. Now you should be quick. You should know that these two can be put together in one single condition. A power M, M greater than N or M less than N is M not equal to N. So this part is a DCFL, it's a well-known DCFL, M not equal to N. Okay, because there is no choice required between these two. After all, a string, either A, whatever string comes, either it will satisfy this or this. This you accept in one final state, this you accept in another final state. No need for any choice. DPDA can easily do this. In fact, we made a DPDA for this in the class. But this part is just regular expression, A plus B whole star, A plus B whole star. Okay. So immediately we can say that this is false. Why? Because this thing, this will not get absorbed here. Because this is A follows B here, B follows A. This type of string will never be here. So these are some extra strings are there. So it's not equal to this. A part of this is equal to this, but it's not equal to this. It's more. In fact, it's a superset. This is superset. Answer is a superset of this. Is it a DCFL? Yes, it's a DCFL. So this is true. This is false. Complement of, what is the complement of A and Bn? A and Bn is nothing but AM, Bn and M is equal to N, right? Complement will be what? M not equal to N, this one. But when you take complement of this, there are two conditions here. One is this, we have complemented. The other condition is all B follows all the A. The complement of that is some A will follow a B. It means BA will be a substring. This also has to be added. In fact, this union, this is nothing but the complement of this. It's a good idea to know the complement of very simple languages, standard language. No need to know the complement of every language. But things like A and Bn, you must know the complement. Okay? It happens to be this. Lastly, is it a CFL? But not, yes, it's a CFL. Every DCFL is CFL. But you can't call a DCFL as a not DCFL. So this is false. So answer is what? 1 and 3. Okay? Let's move to the next question. So a typical question in CFG. This one. So step by, these are all 2 marks questions. You will have to, everything which I am doing today is 2 marks questions. So these are all things which you have to do carefully and systematically. Don't be in a hurry. Just patiently go through it. The wrong answers will be just only slightly wrong. So you have to be careful. You have to solve it precisely. And you must remember all the standard concepts clearly. Okay, now let's move to the next one. Question number 9. Question number 9 I have chosen based on true or false because ambiguity and unambiguous grammars, many true or false questions are coming. Be very thorough with the concept. 9. Which of the following is true? Which of the following is true? Okay. So let's see what this thing is. Which of the following is true? A. Every language has at least one ambiguous grammar. Has at least one ambiguous grammar generating it. Every language has means what? There exists. At least one ambiguous grammar. B says every language has at least one unambiguous grammar. You want to know which is true? Third says every right recursive grammar has an equivalent left recursive grammar and vice versa. D. Right recursion cannot be removed and made into left recursion always, and backwards also. Last is every ambiguous grammar has an equivalent unambiguous grammar for it. This is what we want to do. These are facts that you have to be aware of. First, let's take one by one. This is a slightly tricky one, the first one. Every language has at least one ambiguous grammar. Can you somehow introduce ambiguity if you want? By putting maybe 2 paths. Yes, you can. By randomly putting 2 paths and generating some string. You just have to take any even unambiguous grammar. You can make it ambiguous by simply adding one more path and creating double derivation tree. You may be thinking you can do it always, but you have to be careful. Empty language is an exception. Because empty language, you cannot create an ambiguous grammar. Why? Because ambiguous grammar definitions, in an ambiguous grammar there should be at least one string with 2 or more derivation trees. Empty language has no string at all. So where will you go about in creating double derivation tree for a string? There is no string itself. You can't create an ambiguous grammar for empty language, so this is false. So it's a very tricky one. Empty language will not satisfy this. Other things you can somehow create extra paths and create ambiguous grammar, but so you can't always force an ambiguous grammar. On empty language you can't force an ambiguous grammar. It's all empty language, whatever grammar you make is unambiguous. Okay, it is an unambiguous language, and also not only that, every grammar itself is unambiguous. Here every language has at least one unambiguous grammar. Has at least one. This is also false for some other reason, because here you want unambiguous grammar. What if the language itself is, see, if you here what you say, every language has at least one unambiguous grammar. What if the language itself is ambiguous? There are languages called ambiguous languages, right, for which every grammar is ambiguous. Maybe there are some languages for which whatever you do it will be ambiguous. Such languages exist. So this is false. You can't always guarantee it, at least one unambiguous. You can guarantee this only for an unambiguous language. You can say every unambiguous language has this, but not every language, okay? Because there are ambiguous languages where everything will become ambiguous. This of course can be done. You know, right recursion can be always put on the left and left recursion can be put on the right. You can always create an equivalent. This is just a fact. For every right linear grammar there is an equivalent left linear grammar. not linear, sorry, right recursive. The right recursion can be made into left recursion, and left recursion can be, that means whatever you can do with left recursion, you can do with right recursion, and whatever you can do with right recursion, you can do with left recursion. It's a fact. So this is true. Right recursive grammar can be converted to left recursive grammar, and left recursive grammar can be converted to right recursive grammar. Last, every ambiguous grammar there exists for every ambiguous grammar there exists an equivalent unambiguous grammar. This is false. Why? Because there are some languages which are ambiguous languages. In this case, whatever grammar you write will all be ambiguous. In case this ambiguous grammar generates an ambiguous language, then this is not possible at all. Because if you try to convert it to all are ambiguous, where will you get an equivalent unambiguous grammar? So this is false. Because if you simply say ambiguous, I don't know whether the language is ambiguous or not. In case you say ambiguous grammar, but the language is not ambiguous, then this is true. But who knows, the language may be ambiguous, in which case you can't get any. But here you want, there exists at least one equivalent unambiguous grammar, this is false. Okay, so that's it. So the answer here is C, which is true. So this is very important concept, this keeps coming again and again, so be very clear about this. Particularly the choice A is a bit tricky, so you have to know that the empty language you cannot force ambiguity at all, because there is no string there. So definitions have to be clearly understood to do this type of question. Okay, now let's take the next question. Next question, let's take it up. I have chosen the next question for something to, one common misunderstanding in PDA. I want to remove that misunderstanding so that because it may cause trouble in the exam. Which of the following is decidable? Also, decidability question comes very, very often. Which of the following is decidable? A. Okay, here the question is whether a given PDA on some alphabet, say sigma equal to 0, 1, whether a given PDA accepts some string in the form of WW. Whenever they ask this type of thing, this is an intersection question. That means the PDA's language is having at least one string in this form. Another way of saying is whether this PDA, let's say we call this PDA as M, intersection this language WWW belongs to 0, 1 star is not equal to 5, because there's, what is the meaning of saying accepts at least one string in this form? It means this language intersection, the language of this machine PDA must be non-empty. That means there is some string in this form. That is how you should interpret it. Now you attack this question. Okay, B. Same thing. B is what? Same thing again. Whether a given PDA on the same thing, sigma 0, 1, whether it accepts a string, whose length is even. Here again you can do in the same way. How? See, this you have to do this. They won't give in the question. You have to understand it. How will you do this? LM intersection even length. The language of even length strings, this should be not equal to 5. That means there is at least one string here whose length is even. So it's an intersection question. Whether the intersection of this language PDA and even length string language, is it not equal to 5? C. Whether a given PDA, again a given PDA accepts some string, but only thing now they are asking accept some string in the form of WWR. W belongs to 0, 1 star. How will you do this? Again you can do it like this. LM intersection, this is not equal to 5. All of this is intersection not equal to 5. This means that the PDA accepts some string in this form. Only this WW, this WWR, that's the only difference. Last thing D is whether the language of some given PDA, okay, is acceptable by some Turing machine. They have not given any Turing machine. They have given only the PDA. Whether the language of that PDA is acceptable by some Turing machine. Remember, they have not given any Turing machine. Because if they give both the PDA and Turing machine, it will become equivalence of PDA and Turing machine. That's undecidable. There is something else. Whether is it accepted by some Turing machine? That means is there some Turing machine which will accept the same language accepted by a PDA? Okay, so don't misunderstand that given a PDA and a Turing machine, whether the language accepted by them is equal. That is the equivalence problem. That is undecidable. Now let's see one by one. Clearly the last one, which is decidable, last one is trivially decidable. Of course, whatever language accepted by PDA, there will be some Turing machine which will accept it. Why? Turing machine is more powerful than PDA. Whatever PDA can do, some Turing machine can do it for sure. Trivial. Why do you want to check it? Whatever PDA you say yes, yes, yes. Dumb Turing machine. Trivially decidable. So it's decidable. D. These ones are a bit more tricky. This is PDA, right? And this is what? CSL. So this becomes something like CFL intersection CSL, not empty. Okay. So you can't even construct this thing because this you cannot. See, PDA emptiness is decidable. PDA emptiness, of course, emptiness is decidable, non-emptiness is decidable. But you can't construct this thing because the intersection of CFL and CSL will be a CSL. So for CSL, emptiness problem is not decidable. CSL and above, only the membership problem is decidable. Emptiness is not decidable. So you can't do this. So this is undecidable. Here what happens? This is regular. Even length string is regular. CFL. CFL intersection regulation not empty or empty, both of them are decidable. Why? After all, CFL intersection regular is CFL. Under regular intersection everything is closed. So this becomes PDA, this becomes a CFL. PDA non-emptiness. PDA emptiness decidable, so non-emptiness is also decidable. So it's decidable. This one is what? PDA, that is CFL intersection. This is what? WWR is also CFL. So PDA intersection PDA. CFL intersection CFL, non-empty. The problem is you can't make a PDA for this because CFLs are not closed under intersection. In general, CFL intersection CFL will be in general a CSL. So CSL, the emptiness problem is undecidable. So this is undecidable. And the last one is decidable. So the answer is what? Which of the following is decidable? The answer will be, it will be an MSQ. So the answer will become B and D. In this case, choice B and D is in a multi-select question. Decidable problem. Or they will give Roman numeral 1, 2, 3, 4. It will be 2 and 4 only. Very often they give like that, not as MSQ. But they can give us MSQ also. The answer will be B and D. In this case, the answer is B and D. Okay, so this is a very important question. So the key here is PDA intersection regular is PDA. But PDA intersection PDA is not a PDA and PDA intersection LBA is also not a PDA. Those things, the emptiness problem is not decidable. But PDA intersection regular emptiness or non-emptiness is decidable. Okay, so that's just a thing that many people make mistake in that. Because what they do is they push this regular up. Don't do that. Don't make this into a CFL. Don't make this regular into CFL and say CFL intersection CFL will be a CSL and CSL emptiness is undecidable. Don't say undecidable. It's actually decidable. Regular, don't push it up and make it weak. CFL intersection regular, directly do it. Why do you push it up? Because there's regular intersection is available. CFL intersection regular is CFL and CFL emptiness is decidable. Okay. Remember, this question will also affect questions like this. For example, take this 11 question. I will go through 11 quickly because it's based on the same as 10. Same idea, but you have to know this because it's high probability question. So I'll just quickly do this 11, which is decidable. Again, same concept, but I'm going to frame it in a different way. Given two CFLs, L1 and L2, given whether L1 subset of L2. This is a subset problem for CFLs. This again will depend on the same concept. Similarly, given a CFL L1 and a regular L2, whether L1 is subset of L2. C is given a CFL L1 and regular L2, instead of L1 subset of L2, I am asking L2 subset of L1. Remember, it's not symmetric. This is CFL and that's regular, not symmetric. D. Given two DCFLs, L1 and L2, whether L1 is subset of L2. To do this question, which is decidable or not, which is decidable, the question is which of the following is decidable. To do this, you have to be aware of some facts. First thing, subset problem is decidable only up to regular. Even for DCFL, it is not decidable. Remember, there are two differences between regular decidability and DCFL decidability. What are the two differences? One is subset. Subset problem is decidable for regular, not decidable for DCFL. And intersection, that is whether the intersection, that is disjointedness problem. Decidable for regular, not decidable for DCFL. Otherwise, regular DCFL decidability same as regular decidability. Remember that. It means starting from DCFL, subset problem is not decidable. CFL, CSL, subset problem not decidable. So clearly you can say CFLs. If you give two CFLs, whether subset, this is of course undecidable. Yeah, because even for DCFLs is not decidable. Even DCFLs, subset problem is undecidable. Only if both are regular it's decidable. But there is one more case where it's decidable. What is that? That is the tricky part. Here, many people what they will do, they will push this L2 up and make it CFL, because after all, how do you decide subset? Why is, for example, in regular, if you give two regular language L1, L2, this subset problem is decidable because there is a theorem, if and only if L1 minus L2 is equal to 5. So you can construct this product automata and send it to emptiness. Of course, product automata is available in regular. If both are regular, this L2 bar is regular. Regular is regular is regular. Regular emptiness is decidable. So this is decidable in regular. You can't do this in DCFLs because DCFL are not closed under intersection. So that's the problem. Intersection they are not closed. So this DCFL and DCFL can go even up to CSL. Okay, DCFL and DCFL can go up to CSL. That's the problem. So this thing will not work in DCFL. It will not work in CFL also. So once you know this, now you can see. Now you see you should not push it up. How will you decide it? If and only if L1 minus L2 is not equal to 5. This is a theorem. This will be subset only if the difference is equal to 5. This means L1 to L2 bar should be equal to 5. So what you do, don't push it up, because if you push it up, it will become L1 intersection CFL complement. If you make this regular into CFL, it becomes CFL intersection CFL complement. Then you will say CFL complement is a CSL, and CSL emptiness is not decidable. So you will say undecidable. Don't push it up. Why do you want to weaken it? Leave it as regular. You will get CFL minus regular equal to 5. That means CFL intersection regular complement equal to 5. But regular complement is regular. So this becomes CFL. This is decidable. Like we saw in the last question, CFL intersection regular is empty is actually decidable. Because CFL intersection regular is CFL, so you can construct a PDA. And PDA emptiness is decidable. So this is decidable. Whereas this one, L2 subset of L1, it will be L2 minus L1 is equal to 5. This will become L2 intersection L1 bar. Previously this was regular, but now this L1 is CFL. Now this will become regular intersection CFL bar. Now even if you don't push it up, still it's problem, because CFL complement can go up to CSL, and CSL emptiness is undesirable. So this is undesirable. So it's a tricky question. So the answer is what? Only B is the answer. Which of the following is desirable? Only B. Okay. Now let's move further. So these two questions 10 and 11 are based on a very important concept. Don't push up the regular. When CFL intersection regular comes, don't push it up. Also you should know subset problem has something to do with minus. L1 minus L2 is equal to 5. So subset problem is desirable because of emptiness problem and intersection. So PDA emptiness is decidable, but CSL emptiness is undesirable. So remember that. Okay, now next. So we come to question number 12. So we are coming to the end of this session nearby. So I'll finish out with one PDA and then one this thing, what do you call it? One problem in Turing machine. Okay. Okay, let's take this PDA. Here the question is how many strings, the number of strings, how many strings are there of length at most 10 which are accepted by the following PD, How many? So this is a numerical data type. First we have to find the language and then count how many strings up to the length of 10. Let's see, in PDA very often they give simple ones, either that A power m, B power and m is equal to n, that type of thing, or W says that number of A is equal to number of B, that type of things, or palindromes. In this case you see what it is. The palindrome, this is a slight variation program of the palindrome itself. You should know the palindrome program can be written in so many ways. This is one way, and then further it's given. All these things are written on this loop. Then here on this thing it's written AX epsilon, BY epsilon. And here we have AX epsilon, BY epsilon. And from here it just goes to the, when the end of tape, stack is empty except go to the final state. It's a PDA. See, normally when A comes, we push A, but here the small variation is for A they are pushing X and for B they are pushing a Y. That's all. You should get used to these minor differences. Normally in palindrome program we write just when A comes push A, B comes push B. They have just changed it. And we have used a different state for Z0 separate. There is a starting bit and then after that we use different state. They have used same state. No harm. No harm with that. A Z0 because this is different. This is Z0 and this is X. When A comes the first bit they are pushing it. If B comes they are pushing Y. After that whatever be the bit here X or Y doesn't matter. X becomes XX and Y becomes XY. It means for every A they are pushing X and for every B they are pushing a Y. That's the understanding. And here normally in even palindrome we have left this as a guess. That means leave one bit. Here they have not done that. Directly they have done it. AX. Here itself they start the popping. AX pop. That means they have given a choice here. We have done it by null move choice. They have given direct explicit choice. There is a choice between AX. You can either push it or pop it. This is another way of writing. After all, even palindrome is NPDA. You can either give a choice through null move or direct choice AX XX or AX null. Still even palindrome only. But make sure most people think that this is odd palindrome because you are skipping. This is not skip actually. This is pop. A pops the X. B pops the Y. Here itself you are popping. Then you are continuing the pop. This is not odd palindrome. It will come odd palindrome only if it is AX, X. If you don't, if you skip one bit, then it will become odd palindrome. This is actually even palindrome. So the answer is this even palindrome. So you have to count how many even palindromes of length up to 10. That's easy. You know the formula, right? Even palindrome of length n. What is it? How many even palindromes? It's 2 power n by 2. Alphabet is 2, so 2 power n by 2. This many even palindromes. So count 10, 8, 6 bit. Up to 10, right? So 4 bit, 2 bit. Only thing 0 bit you count. Remember, normally null string is a even palindrome. But this is even palindrome where W belongs to AB plus, not AB star. It doesn't have null string. Notice null string will not be accepted. Minimum 1 bit has to come. XY has to be there. Minimum 1 A has to come. Null string is not accepted. There is no bypath. There is no direct path for null string. Previously when we have null move, null string will be accepted, but now there is no null move. Null string will not be accepted, minimum 1 bit is required. So this is AB plus. That means this is all even palindromes except the null string. So don't count the null string, 0 bit don't count. 2 will be 2 power 2 by 2, 2 power 4 by 2, 2 power 10 by 2 and so on. Add all this 2 power 2 by 2, this is 2 power 1, 2 square, 2 cube and so on up to 2 power 5. 2 power 10 by 2 is 2 power 5. It means something like you have to add 1 plus 2 plus 4 up to 32. You can use geometric progression or just add it. There is only 5 numbers here. 2 power 1 to 2 power 5. Just add it. It will come 62. There will be 62 such strings. Answer is 62. Okay, that is question number 12. Okay, let's now close it out with one more question. I think our 1 or 2 questions more I can do. That's it. We are done. So let me just do some question in Turing machine. Then I can close it out. Turing machine question, chapter 3 question. Which of the following is false? A language L is decidable if and only if L and its complement are both Turing recognizable. L is decidable if and only, we want to know which is false. L is decidable if and only if L and its complement both are Turing recognizable. B, L is undecidable if and only if at least one of L or L bar is not Turing recognizable. C is not Turing recognizable. At least one of them is not Turing recognizable. C is if L is Turing recognizable but not L bar, not its complement, then L is undecidable. D, none of this. This is one-way theorem, this one. See, this is based on the complement, on the concept what? That whenever a language and its complement both are Turing recognizable, that is both are RE, then both will be REC. That's called the L bar theorem. It's based on that. L bar theorem comes very often in the exam. Let's see. You know this theorem, right? L is decidable. REC if and only if both L and L bar are Turing rectness. Turing rectness means what? RE. If both are RE, of course, we know the theorem goes this side, but surely it goes this side also, because if it's REC, of course L and L bar both will be REC, and REC you can call it as RE. So it will go this side, but this side is more important, but both are true. It is true. L is REC if and only if, decidable means REC. If and only if L and L bar both are Turing recognizable means RE. Okay. Decidable means REC. So this is true. Undecidable, what will be the, see, whenever you have a theorem, there is an opposite theorem also, because P biconditional to Q is same as not P biconditional to not Q. You can complement both sides. What is the complement? Decidable is undecidable. Complement of both are Turing recognizable is at least one is not Turing recognizable. At least one is not Turing recognizable. That is a complement. Both are Turing recognizable complements. At least one is not Turing recognizable. So this is also this complement. Not P biconditional not Q is true. This is a bit more tricky. If L is Turing, that means if L is RE but not its complement, what can you say? See, if both are RE, then both will be REC. But what can you say in case that one is RE but the other one is not Turing recognizable? Then this is where you have to do it. How you have to do it? You have to understand that, see, RE is not closed under complement. But you know that there are only two possibilities. RE is either REC or it is RE but not. Only two possibilities. In case it's REC, the complement also will be REC. And of course you can call REC as RE. So that means if L is like this, L bar can only be in the area of inside the RE, that means REC, or it can go totally outside, that is RE but not REC. This is the thing. Then its complement, in case it's like this, L is like this, the complement will be where? Not RE. Because the complement of RE but not REC is always not RE. That means L bar has only two possibilities. So any RE language, there are only two possibilities where it can be. See, this is RE 2 power sigma star. If a language is in RE, its complement L bar has to be either here or here. It can never be here. Okay, complement of RE will be either here or here. There are only two possibilities. But you are saying that the language is here, but the complement is not inside this. That means it's not here. Then it must, where is it then? It has to be in not RE. So not RE. Of course you can call not RE undecidable. Not RE is undecidable, right? Undecidable is much bigger, but nothing wrong in calling not RE as undecidable. Not RE is undecidable. So it's correct. It's weak, but it's correct. So it is true. In fact, more strict thing will be L is not RE. We can surely say that. In case L is RE, but its complement is not RE, then surely the L is, so in this case what is not L, L bar. I made a mistake here. In this case, yeah, L is true. L is undecidable. No. L bar. By mistake I wrote L. It's L bar. If L is Turing but not L bar, then surely what you can say about L bar is surely undecidable, because we know that L bar is in not RE. Not RE can be weakly called as undecidable. By mistake I wrote L, it's actually L bar. Okay. So this is the story, okay, of this thing. Remember, complement of RE has to be only here or here. Okay. Sometimes some textbook call this 1, let's call it 1, 2, 3. This 1 plus 3 is called co-RE. Co-RE means the complement of all RE languages. In the class we didn't do 1 plus 3. We did 1 plus 2 is RE, 2 plus 3 is undecidable, okay, and 2 plus 3 is undecidable, and 1 plus 3, what is it? It's called co-RE. Co-RE means it's a complement of all RE problems. This one area, REC area and not RE area put together is called co-RE. Co-RE means the complement of all RE problems. Okay, that's it. So what is our final answer? That means all these are true. We want to know which is false. The answer is none of these. That means all three are true. Okay. That's it. So we have come to the end of this thing. One last thing I'll just give you and then we'll close it out, because that's based on this co-RE concept. Quickly we'll do it. Which of the following is false? A last one. RE intersection REC equal to REC. We will call, let's call this as RE represents all the RE languages, that is LRE. Let REC represents all the recursive languages. Now which is true? RE intersection REC. It's not, this is the entire area, it's not just, this is not just any RE language, the entire set of RE language. If you want to write L like this. Sometimes the exam they'll just call it RE also, okay, see. Then LRE intersection L not RE equal to phi and DL co-RE. We call co-RE as all the complement of all the RE languages. Intersection L co-RE and L not RE is equal to phi. Sometimes the exam they will just say, instead of writing L not RE, they will say let not RE represents the set of all not RE languages. Same thing, we are writing it L not RE, okay, is equal to phi. In this case, the question is which is false. We can show the answer is D actually. How to do it? The best way to do this problem is draw like this. This one is REC. This RE but not REC we will call it 2, and not RE we will call it, this is 2 power sigma star. Not RE we will call it 3. Now we can see RE intersection REC. That means this 2 intersection REC is what? 1. 2 intersection 1 is REC, of course. 2 intersection, because RE is the whole thing. Sorry, RE is not 2. RE is 1 plus 2. 1 plus 2 intersection 2, 1 will be equal to 1, of course, because RE is both 1 plus 2 is called RE. Okay, so this is true. RE intersection co-RE. RE is what? 2, no, 1 plus 2. Intersection with co-RE is 1 plus 3. What is the intersection? It is 1, that is REC. So this is also true. Next is RE intersection not RE. RE is what? 1 plus 2. Intersection not RE is what? 3. What is this thing? Phi. This is also true. Last is co-RE. Co-RE is 1 plus 3. Intersection not RE is 3. 1 plus 3 intersection 3 should be 3. But they have told phi. So this is false. So clearly answer is D. This is just showing co-RE. I wanted to introduce the idea of co-RE. In the class we didn't do co-RE. Co-RE is actually the complement of all RE is actually 1 plus 3. 1 plus 3 is called co-RE. That is the complement of all RE languages. Okay, RE complement will be either in the REC or it will be in the not RE. It cannot be in the RE but not REC area. Just remember this. Okay, good luck to all of you. Be confident, and if the question is easy, try to do maximum, and question is tough, don't bother. It's, for everyone it will be tough. It's after all a competitive exam. Don't get flustered. Try to do your best. Good luck to all of you. Okay, take care.